A pharmaceutical contract development and manufacturing organization, or CDMO, is a high-volume physical environment. Managing production across creams, gels, and ointments requires tracking thousands of distinct topical SKUs through intricate manufacturing routings. Understanding the enterprise economics of this facility is a massive relational data problem. Every material cost, labor hour, and machine setup time interacts continuously across the entire operation. The industry standard for attempting to solve this problem is Microsoft Excel. Excel is highly effective for isolated modeling, but it breaks under enterprise scale. When you force millions of rows of production data through localized spreadsheet formulas, the architecture fails. Update lags stretch into hours, files crash, and a single broken cell reference corrupts the entire dataset. As repetitive daily tasks multiply to manage these brittle files, the operations team loses visibility. The organization suffers from retroactive operational blindness, only discovering cost overruns weeks after the manufacturing run has ended. Python provides the necessary alternative. In this context, Python operates as a strict structural engineering tool for operational finance, capable of processing massive datasets reliably. The foundational engine behind this architecture is pandas, a data analysis library designed to ingest, relate, and compute large volumes of operational data. We are going to use this library to build a deterministic, automated costing pipeline directly from first principles. Replacing static spreadsheet cells with automated relational joins allows the system to process multi-plant data at a speed that enables proactive bottleneck identification. The raw material for this operational finance pipeline comes directly from isolated data extracts pulled from an enterprise ERP system like SAP. To calculate costs accurately, we must extract specific, highly fragmented data tables. We need the daily production orders, the inventory logs, and capacities for every work center. Attempting to run a financial model on unstandardized data instantly generates unreliable forecasts and inaccurate costing. The math cannot execute if the underlying text is inconsistent. We begin with Python's ingestion phase. We write a script that programmatically reads these raw CSV exports the moment they are generated. The first phase of programmatic cleaning snaps errant text into a cleanly formatted tabular grid structure, a pandas data frame. Next, the script standardizes data points, stripping invisible whitespace. Finally, it converts text strings into computable datetime objects, allowing us to calculate and sort chronologically. Achieving this perfectly typed, standardized data frame is the non-negotiable bedrock required before any complex financial modeling can begin. With a standardized foundation, we map the unit economics. We start with the bill of materials, mapping the exact active ingredients and packaging required to produce one batch of hydrocortisone cream. To calculate this at scale, we use vectorized math. This is Python's primary computational advantage over traditional cell-by-cell formulas. This visual demonstrates array multiplication. Instead of dragging a formula down a column, pandas multiplies the entire array of quantities by the entire array of unit costs and simultaneously generates a complete total cost column. Material cost is only half the equation. Physical manufacturing requires mapping operational routing data to capture the standard hours necessary to produce the batch. We must track the exact time consumed by specific bottleneck operations, dispensing the raw chemicals, mixing the compound, and filling the individual tubes. To link material costs and standard hours, we use the core mechanism of the automated pipeline, relational joins. The pipeline seamlessly merges the production and routing tables, using the product SKU as the relational key. This creates a centralized star schema, linking all distinct manufacturing variables back to a single source of truth. Capturing these exact standard hours programmatically directly dictates how we track labor consumption across the facility. Mapping this runtime mathematically reveals exactly where bottleneck pressure builds up on the manufacturing floor, allowing us to pinpoint constrained capacity. Automating these relational joins allows the financial model to scale across multiple plants and thousands of SKUs without suffering any performance degradation. We now introduce the most volatile variable in the cost model, department-specific labor. Standards labor costs are theoretical. Daily operational instability, staffing shortages, and required overtime constantly destabilize the actual cost of production. To account for the true cost of operating the facility, we must calculate fixed overhead absorption. A CDMO carries massive fixed costs. If a facility costs $7 million to operate annually, that expense must be systematically allocated across the facility based strictly on planned production hours. We build a dynamic calculation that maps an exact hourly absorption rate against the specific runtime required for each individual batch. This exposes a severe EBITDA risk. Lower production volumes immediately trigger underabsorbed overhead. The fixed costs remain, but the units to absorb them vanish, directly destroying profit margins. To track this destruction in real time, we deploy Python's ultimate analytical output, the vectorized variance engine. This graphic displays the standard labor efficiency variance formula, actual hours minus standard hours multiplied by the standard rate. While a spreadsheet applies this cell by cell, the Python engine maps this exact formula across 50,000 production orders in a fraction of a second. This vectorized engine runs on a daily cadence, serving as a radar for operational instability that month-end accounting misses. With the foundation established, the system enables programmatic scenario modeling. Static reporting tells you what you have already lost. Proactive simulation allows you to test operational changes before committing capital. This sequence shows a sensitivity loop. Users can iterate through distinct operational shocks, rapidly simulating a 5, 10, or 15% runtime increase on a specific packaging line and instantly generating the resulting EBITDA impact. Executive operations teams rely on this immediate mathematical feedback loop to execute precise capital expenditure planning and labor forecasting. However, Python code is not meant to replace the executive dashboard. To bridge the gap, we implement the Excel handshake, establishing Excel as the necessary operational financial presentation layer for corporate management. Python acts as the invisible high-horsepower automation engine operating entirely behind the scenes. The final line of the script pushes the fully calculated, perfectly formatted, multi-sheet reports directly back into an Excel workbook for management review. The long-term strategic trade-off is clear. Continuing to scale manual processes ensures failure. Adopting scalable analytics is a mandatory requirement for growth. Without building this automated pipeline first, advanced concepts like manufacturing digital twins or AI-driven forecasting systems are impossible to implement. Mastering Python manufacturing automation transitions the CDMO from logging historical losses to a state where every manufacturing variable can be modeled and optimized.